Hello, everyone. Good morning, good afternoon, and good evening, depending on where you're joining us from today. And welcome to the webinar. My name is Scott Dobbin. I'm the Global Market Manager for UVTech, and I'll be your MC as well as a speaker for today's session. We'll take the next 35 to 40 minutes to share with you some insightful options as it relates to measuring and monitoring BOD, which stands for Biochemical Oxygen Demand, and COD, which stands for Chemical Oxygen Demand. By the end of the session, you should be familiar with how this approach works and if it could work for your facility. Our speakers today are Dr. Karim Kalu, who is the Applications Manager at UVTech and has over 17 years of expertise in water and wastewater analysis, as well as myself, Scott Dobbin, the Global Market Manager for UVTech, who has 12 years of experience with VIS analysis. For today, we'll start with a safety moment and work through till we get to the Q&A session at the end, as Wayne mentioned. And as a reminder, there is that Q&A area to put those questions into. Today's safety moment. This webinar is being recorded, so please make sure you're in a spot to safely listen and watch the presentation. If you are not, we do encourage you to please log out and watch the recording later. So why do we want to monitor for BOD and COD in real time? Typically, plant operators rely on historical data, whether that is information from traditional simple sensors, results from slow to gather composite samples, time of day or time of year, seasonality, to make treatment decisions, which includes a tremendous amount of guesswork, essentially leading to a treatment train that works, but is at risk. Then the process changes. A slug is released or there's a dumping event of something, and those methods that you relied on go out the window. Now your process is not under control and at risk for undertreatment, environmental fees, or bad PR that no one wants to see. With the UVTech portfolio of products, you gain access to the changing nature of the incoming waters with rapid and real-time detection of those events to regain control. So what does this all mean for you? Detect unforeseen events. You don't know what you don't measure. Respond faster. Think time is money. We have customers where their products are literally going down the drain. That is lost revenue. React confidently. Instead of waiting for lab results that take 5+ days, such as with BOD, you can confidently see what is happening in your plant with real-time insights. Save on cost. This allows you to optimize your treatment train for what is coming into the process, reducing chemicals and energy versus a play it safe strategy that is no longer necessary. Assure compliance. These processes run more efficiently when we react confidently and respond quicker, which naturally leads to compliance around regulations. Then ultimately, this leads to improved water quality for everyone. Every minute, every day, no waiting for labs, no reagents. With our focused approach of delivering practical, accurate, and affordable solutions, you can trust your plant will gain the insights you need to make the most informed decisions possible. I'd like to pause here quickly for a poll. If we can get that on the screen, but the question here is, how familiar are you with real-time BOD COD monitoring using UV-Vis? And here we answer either very, somewhat, or unfamiliar. So you should be able to see that on your screen now. So we'll pause for about 20 seconds or so to let you guys put some results in. And then we'll display those results and see where we're at as a group. So maybe 5 more seconds. 3, 2, 1. Okay. Can we see those results now, please? Oh, wow. Okay, great. Well, you guys are, can we see the results on the screen here? If we can't, I think we got 56 unfamiliar, 36 somewhat, and 8 quite unfamiliar. So that's great. So this will be a great segue into the next part of this program with K-Rim, who will give us an understanding of spectrophotometry. So I'll pass it to you, K-Rim.
Thank you, Scott, and thanks again for joining us today. So I will start with the basic measuring principle behind most products that ABB's UV-Tech portfolio has, and that's spectrophotometry. So if we move on to the next slide, spectrophotometry, or we commonly refer to this as UV-VIS absorbance as well. And UV here stands for ultraviolet, and VIS stands for visible light. And it's a very simple principle. I'll explain the details of it, but if you first look at the colored graph in the center of this slide, what we see is that many parameters that are of importance to water quality monitoring absorb UV or visible light. And that's very important to us. If these things absorb light, we should be able to measure them using the absorbance principle. And let's take a closer look. There's those parameters such as BOD, COD, Scott mentioned at the beginning. This is the title of the webinar. So those are for organics measuring, such as TOC, BOD, COD. Those organics absorb strongly in the UV region of the spectrum, which is essentially from 190 nanometers all the way up to 350, 340 nanometers wavelength. On the other side of the graph, we have visible spectrum. So these are essentially the colors that we can see with our own eyes, where we would see the effect of colored compounds absorbing as well as suspended solids, here denoted by turbidity, but what it is essentially suspended solids. There's many other parameters that are not on this graph. There's two more mentioned on the left side. So there's some inorganic compounds as well, such as nitrite, NO2, nitrate, NO3. So all of those absorb light and therefore can be measured using this technique. So how does this technique work? Let's get a little bit into the details of the physical law behind this procedure. So on the right-hand side of this slide, we have the Beer-Lambert law, which tells us the relationship between absorbance and the path length of the measuring cell we use to do our measurements and the concentration of the compound. So I'm going to have a closer look with you into concentration and the path length components of this equation. So let's continue on with the next slide and take a look at how concentration relates to absorbance. So the equation is still there. As you can see, there's a direct proportion. And if you do this test using distilled water and a specific compound, what you will see is that higher the concentration, higher the absorbance. And the relationship is linear. So very simple, very straightforward. Let's take a look at a real world example on the next slide, where we have nitrate as our example compound. And on the left-hand side, you're seeing its absorption profile. So it absorbs light strongly in the shorter wavelengths that are shorter than 230 nanometers. So we see a beautiful absorption profile. And if you were to pick any wavelength where it absorbs and then measure absorbance as you incrementally increase the concentration of the nitrate, what you get is the graph on the right-hand side. So we have, again, as mentioned earlier, that linear relationship. They fit really well. Let's continue on with the next slide and take a look at path length now. Path length is really important too. The measuring cell that you use in your instrument can have various path lengths. And by modifying the path length, because it's also in that equation, we're able to modify how much absorption we can measure. And that brings a lot of versatility because we can use short path lengths to measure very high concentrations. We would typically use these in wastewater applications where we're looking at thousands of milligrams per liter concentration in certain cases. On the other end, on the right-hand side of the slide, we can use long path lengths to increase the instrument sensitivity. In this case, we're talking about applications such as drinking waters or high purity applications, where we're really trying to increase the sensitivity of the device and we're looking at very low concentrations. Let's continue with the next slide and again, look at this with some data. So our nitrate example again, The same product can come in different path length options, as you see in the table. So if you look at just, for instance, a measuring path length of 1 millimeter, you see that the range goes all the way up to 50 milligrams per liter. But if you were to use a path length of 50 millimeters, what you will have is a much lower maximum range, only 1 milligram per liter, but you'll be able to get detail down to the level of 0.02 milligrams per liter. Next slide, please. So let's now talk about BOD, COD, and how VIS comes into this picture, how they relate to one another. So, well, actually, let's first start by why do we measure organics in the first place? Of course, this is really important because organics make up an important portion of what we consider pollution in water. And not only that, but a wastewater treatment plant, what it tries to remove from water is mostly organics as well, along with other things. But one particular challenge with organics is that there's so many different kinds. And literally, we're talking about thousands to maybe a million of them. It's very hard and expensive to measure them individually. It's actually an impossible task, really, to do them individually all by themselves. Therefore, the industry practice is to use aggregate parameters. And these are the ones we've been mentioning: biochemical oxygen demand, BOD, chemical oxygen demand, COD. And another common one is TOC, total organic carbon. Now, so these are aggregate parameters, so they're commonly used in the industry to estimate the organic strength of the water or wastewater sample we have. Just a quick note on TOC, as you might have noticed, the title of this webinar is BOD and COD focused. So it doesn't mean that we don't do TOC. We actively deal with TOC as well. It's very similar to BOD and COD in that context, but it's more common as a surrogate for BOD and COD, especially for treatment operations. That's why we want to keep the focus on BOD, COD. But just again, quick note that TOC is very similar from a detection standpoint using UV-VIS technology. All right, now let's take a closer look at BOD specifically on the next slide. All right, so BOD, as the name implies, is a microbial, a biological test. So it uses microbes or microorganisms to degrade organic matter, and it takes time. So it's very useful because it represents what happens in the environment if you were to discharge wastewater into a river, for instance. But because it's biological, it takes a lot of time. And the standardized BOD test is typically what we call BOD 5. The name implies it, it's a 5-day test. So from a process control standpoint, it's really not very useful if any use at all. Like not much comes out of it from a process control standpoint because it's historical data. Like at the time you get your results, it's already too late to make a change, but it gives us a historical idea about how the plant performed. Another problem with it is that because, again, it's microbiological tests, it doesn't have the best reproducibility. So the standard reported reproducibility for the BOD test is plus minus 15%. If you looked at reference sources such as Standard Methods or American Public Health Authority, that's the number you would get. But it's important to note here that that number is also coming from a very standardized lab test where a synthetic solution is used to represent a certain amount of BOD in the sample. Now, when we think about the complexity of wastewater samples, where there's usually a high level of suspended solids and much more heterogeneous composition, these standard errors might actually be well exceeded with actual samples. Now, let's take a look at COD on the next slide. So COD is an improved version of BOD in some aspects because it's a chemical test, so it's more precise, it's more controlled in that sense. But as it's a chemical method, it uses actually quite hazardous chemicals. So there's mercury and dichromate involved in the testing. And that's not only a problem from a personal safety of the person doing the test, but you have to pay for those chemicals twice almost because you have to pay for the reagents to do the test, but you also have to pay to dispose of them properly because they're not safe to dispose of down the drain. But it is an improvement in terms of how fast you get your results. You get it in 2 to 5 hours, so much faster than BOD. but still, you're not getting the actual in the moment results of what's happening with wastewater quality or your process. Um, it's still delayed information, especially when we consider industrial wastewater, where things can change within minutes. A 2 to 5 hour result, getting results back in 2 to 5 hours is still not that great. It also has improved reproducibility compared to BOD. So the standard reproducibility reported for COD is plus minus 8%. But the same note I mentioned for BOD applies here as well. This is again under very controlled conditions. We check the methodology's reproducibility. In real world samples with wastewater particularly, we might see these numbers exceeded in terms of error margins. All right, now let's take a look at how BOD, COD, TOC, and UV-Vis relate to one another on our next slide. All right, so on the right-hand side, there's a Venn diagram, sort of shows you how they overlap, the groups of organic chemicals that are typically measured under these tests. And you can see that there's a pretty good overlap. As I mentioned earlier, many organic compounds of interest absorb light, and therefore they're measurable using UV-Vis technology. And one very big advantage of UV-Vis, we talked about getting results back in a timely fashion, right? Like one big advantage of UV-Vis is really how quickly you get your results. It's a physical method. All we measure is absorbance, and then we correlate that information to concentration. So the measurement takes very little time. It could be as little as 5 seconds, but you get your results within seconds. So therefore, it has much higher value in terms of taking action with the information. The method also does not use chemicals, so there's no reagents involved, which makes it essentially a simple method. There's no sample conditioning, no sample preservation. You can analyze it on the spot or in real time without any reagents. Another advantage of UV-Vis, it's important to also mention that, is that it provides multidimensional data. And I need to explain this a little bit because it might not mean much if I just say multidimensional. So when you do a BOD or COD test, per test, you get one number, let's say 200 milligrams per liter. So you get your concentration number. With UV-Vis, you will get that number as well. So you have your quantitative total organic concentration number. But because different groups of organics absorb light differently, you can also get information about the composition of organics. So you can break down that total number into components that make up the total. So an example here would be, for us, you'll be able to separate proteins from fats, from the total BOD or COD. So you get more information, more detailed information, or more multidimensional information. All right, so let's continue with the next slide and talk a little bit about sample representation, or how well samples represent your actual process, and some sampling errors a little bit more essentially in detail. So I've touched on these briefly before, but this is a good summary slide in that sense. One problem with the traditional lab methods, whether it's BOD or COD, is that the way you would do the test is you would either go with a grab sample or a composite sample. And this is really important because when you think about it, you need to take a small volume, a finite volume of sample, put it in a container, and then test that. So that's a big limitation in terms of how the testing works, because you get poor temporal representation, right? It's not continuous, it's just a snapshot within a time frame, or poor spatial representation, because you're just grabbing a sample from somewhere in the process and it's a small volume. So there's real problems with representation of what's really happening in the process. Another issue is sampling errors. I touched on this too, but quickly summarizing it. These tests might require, when you collect a sample, you might not be able to analyze it on the spot. You might have to transport it to a lab. Therefore, you might have to condition your sample. You might have to add preservatives, or you might have to store it for some time, and the temperature of storage will be important. So all of these factors add up to the error margin, and sometimes the error margin becomes very large, so that the information is not as useful as it could be. And of course, it goes without saying that there's long turnaround times because of all these processes. All right, now let's look at these concepts with a little bit of data. As we move on to our next slide, we will see so this is real data from the field, from an actual site. We're looking at real-time BOD over a week, and that's the gray line on the figure. So you see there's a lot of change in water quality. It goes up and down quite a bit. And then you have the orange squares on the graph as well. Those are lab samples. Those are grab samples analyzed using the BOD standard BOD test method. And what's really important here is that you will see that there's 7 BOD samples there. So that's 7 samples collected throughout the course of a week. If you got composite samples and if you average this for the entire week, like the number you get is around 211 milligrams per liter. And you will see immediately that that really misses a lot of changes in water quality that are well below that number, and below in the sense that it could be less than half of that number or well above that number, where we would see more than double that number at times. So you're missing a lot of detail, and all of those events, below average numbers, above average numbers, are actually process optimization opportunities that are missed. Now let's move on to the next slide and take a look at some of the error factors as well. So I mentioned for both BOD and COD, yes, there's a standard error that's reported in reference sources, and for COD it's plus minus 8%. But I caution that there might be a higher error involved if we were to deal with actual wastewater samples. And in this particular case, again, we're talking about field data here, where in one field, in one site, we wanted to check the consistency of the lab results. So what we did is we collected a wastewater sample and we split the sample into 2 containers and sent them to 2 different labs. But these are third-party labs that do accredited lab work for COD. And what we've seen in the results was quite interesting, because the standard error is 8%, but for some samples, one sample in particular, if you looked at sample 6, the difference between the 2 labs for the same sample can be as high as 42%, and it shows quite a bit of variation. In some cases it was as low as 2% and sometimes very high. So that's another thing very important to keep in mind. And an issue with even established methods like COD and BOD being analyzed in a third-party lab. Now let's move on to our next slide and talk about monitoring. Sorry, very quickly, this section. So now we're going to move into, okay, we talked about the principles and BOD, COD, and how the technology does it. Now we're bringing it all together and taking a look at the technology platform and how it essentially fills this need. So let's start with the first slide. All right, when we look at the market space for products that use not just UV tech, but any product that essentially uses this technology, and there's a lot of them, what we will typically see is that there's basic products, which you see on the bottom left corner of this figure, that we use 1 to 2 wavelengths. So you measure absorbance at 1 or 2 wavelengths, and these are rather simple sensors. So they're low cost, but they come with limited detection capabilities. And they would typically be used for looking at something like UV254, which is absorbance at that wavelength, or color, or suspended solids. They can sometimes be used for parameters like BOD, COD as well, but usually the information is not very accurate. So what you would get is more so trending information. On the other end, the top right of the figure, you would have the more advanced sensors. These are typically full spectrum sensors, which means they look at absorbance at sometimes hundreds of wavelengths. So they get a lot of information. Therefore, they have much more of an increased detection capability, but they also come at an increased cost and sometimes a bit of an increased complexity in terms of maintaining and calibrating the instrument as well. So let's move on to the next slide, because it shows us something interesting. What we've realized is that, okay, so there's these 2 groups of products which we offer in our product portfolio as well, like everybody else, but we've seen a big gap in the middle. So what about we come up with products that kind of optimize the simplicity and low cost of simpler sensors and the detection capabilities of more advanced sensors, and offer those as well. Because really, at the end of the day, the product has to fit the application. And every application has different needs, and we're going to talk about these briefly in the coming slides as well. But that's really important to realize that, the most advanced sensor may not be the best sensor for the application, or the lowest cost sensor may not be the best fit for the application. That's really important to keep in mind, that every application has unique needs. All right, let's move on to the next slide and take a look at the idea behind the mid-tier products with an illustrative figure. So this is only an illustration, but this comes from essentially our observations throughout the years from the field data. What we've noticed is that, for many applications, if you're looking at parameters like BOD and COD, we get a lot of information out of a couple of wavelengths that are carefully selected. That gives us pretty much a similar accuracy to a full spectrum device. So in this figure, you see, sorry, the slides moved back. If you can go back to the illustration figure, I'm not sure. Oh, no, we're going back in slides. If you can go forward to the illustration figure. All right, perfect. We're back to our illustration figure. Sorry about that. Now, if you look at this figure, going from one wavelength to two wavelengths, you gain a lot in accuracy. And if you continue with three wavelengths, you gain even more, four wavelengths, even more so. But you will realize it's a diminishing returns curve. And if you keep adding more, you won't get much of an improvement. So this is really the idea behind our mid-tier products, where we can gain as much as we can out of a full spectrum device, yet keep the instrument complexity as low as possible. Now let's take a look at actual data that further illustrates this on the next slide. So now we're looking at data from the field. We're comparing a 2-wavelength system for doing BOD measurement and a 4-wavelength system for doing BOD measurement. And the data is from the same site. So for those of you who may not be familiar with regression analysis, so the R-squared number you see at the bottom right corner of each graph, that tells us how close we are to a perfect relationship. So here, a perfect relationship essentially means the sensor's BOD numbers match the lab numbers perfectly. And that number needs to be 1 for a perfect match. So the closer it gets to 1, the better the correlation is. And as you can see, going from 2 wavelengths to 4 wavelengths for wastewater BOD application, we gain a lot in accuracy. This is by no means to say 2-wavelength systems can never be used for this application. You would get some trending information, but your accuracy would be relatively poor. So you may not get process control information out of that. Now let's move on to the next slide and talk about what I've mentioned briefly. So matching sensors with objective. As I keep repeating a few times, there is potential for trending monitoring, by which what we mean is that you're not looking for very accurate numbers, but you're looking for trending. So is my BOD going up? Is it increasing? Is it decreasing? Is it staying stable? So that's one way of benefiting from these sensors. This might be all a particular end user needs for their monitoring purposes. The advantage of this is that these will be simpler sensors with very low maintenance and low to no calibration requirements, essentially, but your accuracy will be poor. In the middle, we have process control purposes. This is sort of like you need more accuracy at this point because you might be controlling your dosing algorithm, your aeration rates, etc., but you're making process decisions. So we definitely need more accuracy. And that comes with maybe slightly increased maintenance potentially for the sensor itself. And on the other end of this, we have compliance monitoring, which obviously requires very high accuracy, but that comes with an increased cost in terms of maintenance. Especially, you might need to calibrate your sensor frequently, again, depending on the conditions. All right, let's take a look at the next slide. And it's really important to ask these questions when we're talking about sensors and their fit to application. What is an acceptable measurement for our monitoring purposes? What is the accuracy expected from the sensor? And this is really important because, usually we think, oh, the higher the accuracy, the better it is. Obviously, knowing something accurately is always important. But what we really mean here is, if the sensor gives you plus minus 1 milligram per liter level BOD detail. Is there really much you can do with that in terms of process control? And in most cases, actually, there's not much that can be done with such small variations in organic strength or BOD load. And depending on the application, you might be interested in tens of milligrams per liter changes, hundreds of milligrams per liter changes. It really depends on the application, and different sensors fit different needs. What's required for the control system is also important. That's really process control. What can be done with that information is an important question to address. And last but not least, how fast does the measurement need to be? Earlier, I mentioned in some industrial wastewater applications, changes happen within minutes. Sometimes those changes last only for a few minutes too, but the change is so big that the effects are still overwhelming for a treatment operation standpoint. Therefore, if your measurement frequency or the speed at which what you're using doesn't report within a few minutes or sometimes in a few seconds, you will miss those very important events. Whereas in some cases, the wastewater might change very gradually, and therefore that might not be needed. All right, so this brings us to our second poll of the day. So we'll have another. Oh, I apologize. I had one more slide. Very sorry about that. As always, I like showing a bit of data to explain the concepts I just explained. So we have here the left and the right-hand side figures. They compare two situations, factory calibration versus site-specific calibration. This really touches on what I was saying in terms of you might get trending or you might want to get more accuracy. So let's look at the left-hand side graph first. So all the sensors in the UV Tech portfolio come with factory calibration. So your device will trend. And as you can see with the red and blue lines there, the upward and downward trends are following each other, but the accuracy is not quite there. So this is one possible case when you stick with a factory calibration. Mind you, in some cases, they will match very well right off the bat. That's also possible. But just to demonstrate here what we mean by trending and what you get out of it. When you compare this with the right-hand side graph, which is site calibrated, so that's the highest accuracy we will get out of sensors if we calibrate them to the site-specific conditions, you will get a much more closely matching graph, so we have much more increased accuracy there. All right, now let's continue with our next slide, which is essentially our second quick poll.
Yeah, thanks, Kirim. Okay, everybody. So one more quick poll time here. If we can get that going, but do you see value in measuring BOD and COD in real time? And three possible answers here: yes, no, and don't know. So we'll give this about 20 seconds for people to program an answer into the poll here. Some great feedback from Kirim on the background of this technology and the usefulness of real-time detection. So give it about 5 more seconds. 3, 2, 1. Okay. Can we see those results, please? Okay. Overwhelming yes, 82%. Okay. Few with no and a few more with don't know. So okay, that's great. Great feedback. I think that's great to show what the value is for this sort of detection capability. Okay, now let's take a look at some of the products that are available within the UV Tech portfolio. First, some background on where this technology came from. As some of you may or may not know, UV Tech is the new portfolio name given to the Realtek Inc. products that ABB acquired back in February 2024. These now live in ABB's CWA, Continuous Water Analysis family of products. We start with our field meter for rapid BOD and COD readings. This is a small lunchbox size item that you can take it where you need it to go, whether that's into the field or within the lab. You have the flexibility with a built-in battery pack to truly make it portable. This meter has some great features, which includes no reagents, readings in as little as 5 seconds versus 5 days, storage for 10 data models within the device memory, a micro USB connection to your PC for swapping out data models or extracting sample readings to build or expand new locations or develop new data model profiles. This device is a great entry-level product to show you the capabilities of how we use UV-Vis for BOD and COD. Next, we look at our very configurable and modular products that make up our real-time devices. This selection process takes a very logical approach where you choose a sensor that meets your BOD and COD needs and expectations around accuracy and performance, which includes short path lengths to more traditional ones. Then you select a controller. Here you have two UVTech product options that allow for a different user experience with a built-in graphical PC to a more simplistic LCD numerical display. Both feature analog and digital communication protocols depending on your plant needs. Then you look at the accessories available. This is where the instrument truly becomes more valuable as it helps to reduce the number of manual cleanings needed. Think fewer operator trips to the site and lower labor costs. With our integrated options such as chemical cleaning, air cleaning, and water cleaning. Additionally, we have options to pump a sample to the instrument or take two streams into a single sensor with our dual feed system. Lastly, we marry up the hardware with our liquid AI services. To take a closer look at the sensor selection process, we have two offerings in the real-time category, bypass and probe. Some advantages with the bypass are it allows for more chemical cleaning options to really target the specific fouling agent, more options for path lengths, and the ability to measure two streams in one device with our dual feed approach, as mentioned. On the other hand, probes are easy to understand. You pop them in the water. They're easy to clean with a special cleaning tool, some chemical, and some elbow grease. They also have a small footprint and offer various mounting options. So depending on your application, one may make more sense than the other. Speaking of path lengths, our 1000 series can deal with high TSS and high pressure systems with a stainless steel flow cell and quartz inserts, while our traditional sensors have options from 0.5 millimeter up to 150 millimeter. Think dirtier the water, the smaller the flow cell. And depending on your application and the goals, this will guide your decisions that are made here. When we take a closer look at the accessories, sensor fouling is inevitable. And with the UVTech modular approach, we have various options to address the specific sources of that fouling. Here's a great example from the field where the UVTech sensor maintained a stable baseline, which did not cause an increase in the sensor readings, as you can see on the left side here of the graph on the screen, while the competitor's sensor slowly pushed up as the sensor fouled, as seen on the right graph. This highlights how the automatic chemical cleaning system maintained a very reliable parameter output for the customer, reducing the labor costs and the need to recalibrate. Now for the data services. This is where the magic happens. Depending on the BOD/COD product selected, we offer our Liquid AI data management software for customers who enjoy a more do-it-yourself approach with our field meters. And for the real-time devices, we support the data model creation process with a dedicated service called Liquid AI Calibration Health to build the most robust profile for your facility. Or we can trend right out of the box. The choice is yours. We also offer remote monitoring dashboards for the convenience of seeing your data outside the plant on demand via a secure web-based platform. As you can now see, the UVTech portfolio has many different installation options, from bypass with pressure to bypass with no pressure, to bypass with high pressure, high solids, to the probes with dip style mounting, tri-clamp, and chain mounting options. There is a configuration that can meet your needs. And to tie this all together, proper water treatment requires good, reliable data that you can trust. Having real-time readings allow for actionable insights to drive operational excellence, lower costs, and achieve improved water quality. With ABB's UV Tech portfolio, you can take control and know what's in your water. Thank you, and that concludes the presentation. We'll now take a moment and pull up the Q&A section, Kirim,
Yep.
and see if we can work through some of these questions that popped up. So
Yep.
you
Absolutely.
have
And
one.
we got really good questions, and there's many of them, so we'll try to answer as many as we can live. But we will get back to the questions we could. If you cannot get back to all of them, we will definitely get back to you later on. And if you come up with a question after the webinar, please feel free to reach out to us. We're always happy to answer questions. So I will start with, they're all very good questions, so I'll actually go in order. The first one I see up here is from Louis, and it says, this UV-VIS method is validated, approved by standard methods. So the short answer to that for BOD and COD monitoring, no, it's not. It's not an approved standard method. It's really meant for process control more so than regulatory monitoring. So, you know, that's important to realize and note. But when it's used for instance, nitrate, NO3, there's actually standard method that acknowledges UV-VIS, or more correctly, UV light use for monitoring nitrate. So it depends a little bit on the parameter too. But just because our focus is on BOD and COD, I want to make it very clear it's not a standard methods approved method. And it's really meant for more process control than regulatory monitoring. That said, around the world, there are jurisdictions which recognize this method as an approved method, and in some countries it can be used for regulatory monitoring as well. But in most jurisdictions around the world, it's not a regulatory approved method for monitoring. Right?
Yeah, that's a
So
good one.
I
Um,
can,
Go ahead, Kirim.
sorry, Scott, I thought you wanted to add something. I apologize. You can go ahead.
No, and I think you touched on it a little bit, but there are some markets that have used this as a regulatory approved method. But that is also something that we've had conversations with other EPA and other regulatory bodies of looking at this as something of interest down the road. But currently, as you said, not approved in many areas beyond for process control tools. I do have one here asking about the outputs from Emmanuel. Is the output in milliamp? So yes, the outputs, as mentioned during the product section, come in various forms, digital and analog. So we do output a 4 to 20 milliamp as an option for the parameter readings that can be scaled for the plan, but also other digital and dry contacts and things like that. So you can find more details of that on the data sheets that are available on the ABB website as well. So hopefully that addresses that question.
Right. And I have one here from Emmanuel. And the question is, what effect does turbidity have on the measurement? That's a great question. When we talk about wastewater specifically, of course, there is suspended solids. And when we talk about potable water applications, you might refer to it as turbidity. But turbidity or TSS, whichever way we refer to it, suspended solids, can affect the readings. But that said, there's many ways we compensate for the effect of turbidity or suspended solids. So typically, there's always an extra wavelength in our systems, even in the most simple ones, that will take into effect where solids absorb, but nothing else does. And using that information, we compensate for the effect of solids on essentially the parameters that we actually want to measure. So there is an impact, but it's well compensated for. And I also want to mention, of course, sometimes the site-specific conditions might get very challenging. You might have very, very high levels. Of course, that needs to be taken into account. For instance, if your turbidity is very high, you might not be able to use a very long path length instrument. So that means you might not be able to get very low concentration sensitive readings out of the sensor. So there might be a bit of a compromise there. But in most cases, it's well compensated for and it's accounted for, so it doesn't have any practical effect on the product.
Great. We have one from an anonymous attendee, but how often does the sensor surface need to be cleaned in normal wastewater influent? So I think this is a really good question in general. Obviously, it does depend. Our recommendation is to manually clean a sensor about once a week. And after a few weeks, reassess how frequently that needs to happen. In some scenarios, that has to happen more frequently um, or less frequently. So there's variables such as which automatic cleaning system do they have? What is the flow of the water? Sometimes we see that a good amount of flow will actually keep the sensor cleaner longer without any kind of manual intervention beyond the automatic cleaning systems. Um, but also it depends on what products are running through there. So if we have municipal customers, that those organics look different. What else is in the water? From industrial customers, say dairies or pulp and papers facilities, these do impact obviously the fouling rate. So as a generalization, once a week manual cleaning with the addition of automatic cleaning, whether it's chemicals, which also we have a series of different cleaning solutions to address the fouling agent, as you might remember from the presentation. So if it's biofouling, we might recommend one thing. If it's minerals, we recommend another thing. And we do provide some guidance based off that in our documentation. So there's not, unfortunately, a one size fit all for this, but with the mechanisms that we have and the cleaning solutions and the systems that are available, you should be confident that once a week is a good starting point and we reassess from there. So long-winded answer, but it's not a one size fits all, unfortunately.
Yeah, and I'll quickly touch on that the automatic cleaning systems we provide are quite versatile. As Scott mentioned, we have different approaches, whether it's chemical cleaning, pressurized air, or water. The cleaning system, the automatic cleaning system is also adjustable. So how frequently it cleans the sensor can also be adjusted based on your site-specific needs and conditions. So that's important to note. Another thing is that when we talk about manual cleaning, I think it's important to note this, that it's not really a demanding operation. When we talk about our probes, for instance, we really talk about a 5-minute, maximum 10 minutes kind of cleaning operation. So it's not a long process. It's essentially just taking the probe out and giving it a wipe and then putting it back in. It's not a complex process. There's a question from Fernanda here that says, would the measurement response speed, would it change if you considered 1, 2, or 4 wavelength, or independent of the select model, is it the same response time? So between 1, 2, 4 wavelength systems, it won't really significantly change anything. Those all essentially update the readings between 5 and 10 seconds. So you get really fast results. If you were to choose spectrum probe, though, they do take a little bit longer because they essentially scan hundreds of wavelengths rather than 1 to 4. But even then, we're talking about the readings get updated essentially within a minute or so. So it doesn't make it much longer, but there's a bit of a difference depending on the product because of that. But to answer your question specifically, between 1, 2, and 4 wavelength options, no, there won't be a change in response speed.
Okay, we got one from Jason. How often do lamps, LEDs need to be replaced? So across our portfolio, we use a variety of different lamps from deuterium to tungsten to xenon to low pressure mercury to the LEDs as mentioned here, and typically used in this application are the LEDs with the multi-wave approach. So LEDs have a similar lamp life to what you'd see in a residential or commercial lighting application. So right now we have sensor indicators within the product that will tell us when those lights are starting to fade. So we're anticipating these should last, in the range of 5 to 10 years, but it is subject to the conditions and the application. But the LED lamp life would fall into that similar category, where the others have adjustables between 1 to 2 years, where deuterium has to be replaced almost every 6 months when it's used in a continuous fashion. So for the question, I think I hopefully addressed that for you there, Jason.
Right. Here's a question from Frank. Can you quickly explain how the site-specific calibration takes place? And I think this question came a little bit early in the sense that Scott explained this a little bit after the question was submitted. Maybe that answered it partially, but I will definitely answer it in more detail right now. So site-specific calibration is done through our data analysis services. So in addition to the sensors, we also provide data analysis services. And what happens is that the sensor, as mentioned in the presentation, comes with a factory calibration. So it already has in place a calibration that we even customize based on industry. So it's not a generic one that goes everywhere, but it's more specific to your industry. So it already has it in place. But if you need site-specific calibration, we have a service called Liquid AI, which offers different types of calibration services. And what happens is the sensor gets installed, and we take a look at the data from the sensor, and we determine like good operational conditions. We look at the variations in the water quality, because this is a real-time sensor now, it shows the variations, right? And then we would recommend a sample collection schedule, and we will collect samples at various times throughout the day and throughout various days throughout the week. And then using that calibration set, the sensor will be calibrated to the site. And in this whole operation, all the data analysis is taken care of by ABB UV Tech team. But the sample collection and analysis of the samples is conducted by the client.
Okay. We have another one from Anonymous here. It says, in the invitation, you mentioned wastewater. Does it mean we cannot use it for potable water or other types of fluids? Yeah, no, great question. I think Kirim touched on it a little bit with his introduction of TOC, total organic carbon. So this technology has a lot of different use cases, and we have a full parameter list of things that we can detect using this technique. So for potable water, TOC is a common one. Also, simple UV254 as an indicator of aromatic organics for drinking water applications is quite common as well. So this technology has multiple different use cases depending on the application, the water we're looking at. And we do have a full list of some of those parameters on the website and products that are branded specifically for those different things. So whether that's nitrates or permanganates or a whole series of different compounds that UV-Vis has utility for. So that is available there.
Yeah, and I'll quickly add the question at the very end says other types of fluids as well. And that, of course, that's also possible. As long as you can operate an optical sensor in the fluid, there's a potential for measurement. And what I mean by that is, of course, if it's a very thick liquid, you know, that an optical sensor wouldn't be able to operate in, high viscosity, etc. So, you know, when we say fluid, it can mean many things. But if you're talking about liquids that transmit light to some extent, then you can use this technology to detect absorbing compounds in that particular environment. So it does not have to be water per se. It could be different types of fluids. There's a question from Martin about what is the pH range of application? This is a good question because pH affects everything with water chemistry, and therefore it has an impact on these readings too. And depending on the parameter we're monitoring, it might have a very big impact or it might have a small impact. So just in general, we don't have a pH limitation for the sensor to work. But what might happen is that if the pH changes too much and if it affects how we measure the organics. And again, this is very site specific, so it may or may not happen depending on the conditions. What we can do is we can combine the information from our sensor with a pH sensor, and therefore we will account for the effect that pH has on our readings. So in that way, we can, even if the pH varies a lot and impacts the readings, we can account for that and give you readings accordingly. So in that sense, it won't be an issue. Of course, if your pH is extremely low, and here what I mean is if it's consistently below 4 or consistently above 11, so very alkaline or very acidic, then we might have to consider the form factor of the unit. Like, not all products might be suitable just because of the corrosivity of the water. But it all depends on the pH levels as well as the exposure time, because sometimes we have from chemical cleaning operations, at times during the day we would get very low pH water, but the exposure time is very short, so that's not an issue. But again, everything's very application specific, but we usually accommodate pH pretty well, so it's not an issue typically.
Okay, maybe one last question that I see here: maximum temperature the sensor works in. So I would encourage you to check our spec sheets because it does vary by product type and form factor, and use those tools that are available on the ABB website to see what would be suitable for your application. So just conscious of time here, and any other questions that we didn't get to, we'll attempt to answer those as Cameron mentioned after this session. So I think that concludes that, if I'm not mistaken. And thank you everybody for your time and attention today.